Applying rules 1 and 2. Rule number 1 says to undo a mathematical operation, you must do the opposite. So here we have an equation 8 equals d divided by 10, and we're trying to solve for d. So we need to think of the opposite operation of dividing by 10, since we're trying to undo the dividing by 10. Rule number 2 says that you can do anything you want except divide by 0 to one side of an equation as long as you do the same to the other. So here, if we're trying to undo d divided by 10, the opposite would be to multiply by 10. And since we want to use rule number 2, we also need to multiply both sides by 10, which we can see down here. If we're multiplying both sides by 10, that is now undoing the dividing by 10 and leaving us with 80 equals d. This equation is now solved for d, even though it's on the right. Now, traditionally, as we'll see with rule number 4, we can always switch the left and the right sides of an equation because typically it's more common to see the variable on the left-hand side. So we're just literally, the equation sign stays in the middle, and we're switching the variable and the 80. So 80 equals d is the same thing as d equals 80. Again, both equations are technically solved for d. It's just more common practice to see the variable on the left-hand side. When solving equations, the goal is always to isolate the variable on one side of the equation in order to determine its value, and that's the value that makes the equation true. So, for example, x plus 7 equals 32. Our goal is to get x, the variable, by itself on one side of the equal sign. So here, we really need to use inverse operations, or those opposite operations, to do that, to solve for a variable on one side. For example, the equation here was adding 7 to both sides. So we need to think of the inverse, or the opposite, of adding 7. Well, the inverse of adding 7 would be to subtract 7. That would be the inverse operation to help us get x by itself. So here we have the first one, y plus 7 equals 14. If our current operation is adding 7, our inverse would be the opposite of adding, which would be to subtract 7. Here we have b is a minus 21 equals 10. The current operation is subtracting 21. So we need to do the inverse, or the opposite, of subtracting 21, which would be to add 21. In c, we have 5 times s, or 5s equals 25. We have a current operation of multiplication, multiplying by 5. So we need to do the opposite of multiplying, which is divide by 5. And in d, we have x divided by 12 equals 5. So current operation is dividing by 12. The inverse would be to multiply by 12. Now, the previous slide we just talked about addressed inverse operations. Those were those opposite operations used to isolate each variable because we're eventually going to try and solve. But let's take a look now at each of those same 4 equations and decide whether this new method works also. So before we had a plus 7 equals 14, we had subtracting 7, but let's think about, what about adding negative 7? Would that be the same? Would that have the same results? If I add negative 7, 7 plus negative 7 is 0 and cancels out. So that would work. So I can add negative 7 to both sides to isolate the variable. With a minus 21 equals 10, our inverse was adding 21. Well, is that the same as subtracting a negative 21? So if I subtract a negative 21, well, subtracting a negative really is adding 21. So negative 21 minus a negative 21 would add to 0. So we can subtract a negative 21 from both sides and isolate the variable. with 5s equals 25, we were dividing by 5, but we could also multiply by 1/5. Let's see. If I multiply by 1/5, 1/5 times 5 is 1, and that essentially cancels out. So I can multiply by 1/5 on both sides to get the variable by itself. And finally, if I have x divided by 12 equals 5, instead of multiplying by 12, I could divide by 1/12. Well, dividing by 1/12, we can't divide by fractions, so we multiply by the reciprocal of 12 over 1, which would cancel out dividing by 12. So multiplying by 12 over 1 has that desired effect. So really, the point of this slide is just to show you that those inverse operations are the same. There's multiple approaches to it. Sometimes you can have the same operation, but then you have to change the sign of the number, or you have to take a reciprocal. It's just really what you see, what you're more comfortable seeing, and how you're going to reach your goal. Your goal is always to isolate the variable. It's just good to know you have multiple approaches on how to do that. Now we can take a look about how Kendra and Ted did that. So think about how to solve c minus 3 equals 12. So which method is quicker and why? Let's look at each method. We have Kendra is adding, she added 3 to each side of the equation. So here we have adding 3, cancels out with minus 3, and got c equals 15. So here Ted subtracted 12 from each side and then added 15 to each side. Both are arriving at c equals 15, but which would be quicker? Hopefully you can see Kendra's method would be quicker. In just one step, she solved and got our answer. Ted isn't wrong, but he needed 2 steps versus 1. So there's a lot of different things to think about with using the inverse operations, as long as we're always reaching our goal of isolating the variable when solving an equation.